Today we're working on limits of rational functions. Before we start doing any examples, I want to talk to you about this pretty little chart I've created and the image to go along with it, the graphs that go along with it. So let's say that I'm trying to find the left-hand limit of any rational function right here with an odd exponent. So odd exponent could be to the power of 1, to the power of 3, and we're going to graph a couple so you can see what we're talking about. So when we look at the graph, we're approaching that certain number, whatever that is. You know that number is going to be the vertical asymptote right there, like we have. So if we're approaching that from the left, it's always going to end up being the negative infinity right there. If we are approaching from the right, it would be from the right there, it would be positive infinity because it's going up. Okay, so let's say, and I'll punch in a just cubed right there just because. So you will see what the graph does. So it's slightly different, but it's the same outcome. So it's approaching the vertical asymptote right there. So if it's approaching from the left, it's going toward negative infinity. And if it's approaching from the right, it's going toward positive infinity. So that's where these two come from. Now, what if the exponent is even? So I will go ahead and change that there to just squared, just so we will see the difference on the graph and what it looks like. So approaching from the left, it goes ahead and it approaches the vertical asymptote that is there toward infinity. And it doesn't matter if it's approaching from the left or approaching from the right. It's, in either case, it's going toward infinity. That's where the chart comes from. What can I do with it? So here we are. We have the limit as x approaches -5 from the left. So before I start doing anything, I have to find the vertical asymptote. So the vertical asymptote is what makes your denominator equal 0. So x plus 5 equals 0, and then you solve for x, yada yada. So the vertical asymptote is x equals -5. So it's that vertical line right there, -5. That's your vertical asymptote. That's what makes the denominator equal 0. Okay, that's great. Now, I will split that up into limits. One is the limit as x approaches -5 from the left of the numerator, 7x minus 5. And then the other one is x approaches -5 also from the left of this one, x plus 5 to the 8th power. Because I know if I have this isolated, I can go back to my chart and figure it out what I'm going to do here, if it's positive infinity or negative infinity. But it's where my vertical asymptote is happening right there. Okay, so now at this point, I can just do direct substitution here. So 7, replace -5 right there for x. And then here, I have a left-hand limit. So I'm looking at this column right here, and it is an even exponent. So even exponent, voila, positive infinity. So right here I have -35 minus 5, that's -40, times positive infinity. Because the signs are different, then your final answer is negative infinity. Now, same idea we're going to do for example 2. Before I start doing anything, go ahead and you find the vertical asymptote. So, easy money right there. So the vertical asymptote is 0. Okay, I will split that up like I did in example 1. So the limit as x approaches 0 from the left of the numerator, and the limit as x approaches 0 from the left from the denominator. So the denominator right here, I know this exponent is odd. So let's look at our chart. Left hand, odd, so negative infinity for this part of my limit. So negative infinity for my part of this part of the limit. And now in this case, I will do direct substitution. So 0 minus 8 is negative 8. Compare the signs are the same, therefore positive infinity. So it is so not bad. Last one, we have, ooh, what is this? Okay, vertical asymptote. We have two numbers that make the denominator equal 0. One, x is 5. The other one, x is 4. Okay, here's the kicker. If you don't know which one you're going to split up, look at what x is approaching. So x is approaching 4. Okay, so that's going to determine how I'm going to split up my limit. So the limit as x approaches 4 of numerator, and this one I'm not going to split up because I can plug in 4 right there and it doesn't give me 0. So I'm just going to leave this denominator alone with that part. And then the other limit is x approaches 4 of 1 x minus 4 to the 7th power. 7th power, that's an odd power. Even, odd power. Is that right hand or is it left hand? Well, I don't know because it doesn't tell me. That means I have to find both. And I'm going to put this on hold for now. So from here, I will open left hand limit. So it's the limit as x approaches 4 from the left. So 1x minus 4 to the 7th power. Now I have something. Now go back to the chart. I have left hand limit and the odd exponent. So negative infinity. So now right hand limit. So the limit as x approaches 4 from the right of 1 over x minus 4 to the 7th power. So right hand limit, exponent is odd, so positive infinity. Uh-oh. Now, for a two-sided limit to exist, the left hand and the right hand limits must agree. And in this case, they don't agree. So that means this limit right here doesn't exist. Doesn't exist. So D and E, because left and right hand limits don't agree. Now, at this point, you already know that this limit doesn't exist. There's no point for you to keep working and finding this limit, and it's going to be a D&E, period. You don't get a cookie for working hard. Okay? So now, if you want, but you don't have to, you could move on and go evaluate this limit by substitution. But why would you do that though? Okay? You don't. I mean, waste of time here, but it's fine. Since we're here, negative 24, 22, 22 over 1 is negative 22, and still D&E just because. So at this point that you already determined that this limit doesn't exist, there's no reason for you to continue this. And just make sure you justify that you understand that the two limits don't agree, therefore the limit as x approaches 4 doesn't exist.